Okay, we will start now.
Yep, sure.
Oh, just welcome everyone. So, hello everyone. Welcome to Network Seminar Series hosted by the Center for Network Intelligence of the ECE and RTCCPS IASC. It's my pleasure to introduce today's speaker, Professor Vinayak Naik. He will be speaking on model assisted optimal control for split air conditioners. Professor Vinayak Naik is an Opera Awardee Professor of Computer Science at BITS Pilani, Goa. He is a faculty member at AppCare, a center of excellence in artificial intelligence at BITS Pilani. He received his PhD in CSC from Ohio State University in 2006 and BE in CS from BJTI Mumbai in 1999. He's a member of the Research Advisory Council of D.Y. Patil International University, Pune. Before joining BITS Pilani, he was with IIIT Delhi, IISc, and UCL. He was a research advisor to the CTO of TCS and a member of the governing council of Niti Technology Business Incubator at the Indian Institute of Public Health, Gandhinagar. As a visitor, he spent time as an associate professor at IIT Bombay, a researcher at Microsoft Research, and a researcher at VMware R&D. He was felicitated with Gandhian Young Technological Innovation Award 2016 for using mobile and sensors for healthcare. We request the audience to keep your microphone silent for the duration of the talk, except while asking questions. Please feel free to unmute yourself and ask your questions directly or type them in the chat box and we will relay them. Over to you, Professor.
Thank you for the introduction and inviting me to give a talk. So today's topic is going to be controlling the air conditioners. And I'm going to talk about split ACs, which is typically what we find today. It used to be window-based AC. If you remember about 20 years back, in uh, every room where we used to have an AC, there used to be a near the window we will open up, and then the entire unit used to be one, which means the compressor, the fan, everything was one unit, and then that creates a hole in the big hole in the room. But today, most of the developed countries, we have moved into the model of split ACs. Now, what's the split part in this air conditioners? The split part is there are two. We split this AC into two. One is a fan, which is indoor, and another one is the compressor and the circulation, which is outdoor, okay, which is kept outside the room. And uh, so now that is the model, and I'm showing you the picture of the campus here. So let's proceed. So what is a cooling of the system? So cooling systems, let me just make it small so that I can read. Okay, cooling systems. So these provide us with the thermal control. And I mean, the idea is as the global warming is increasing, we will find the human, we are not used to this increase in the temperature in every season. I know in Bangalore now, right, pretty much we require ACs the whole duration of the year. So with global warming, the temperature is increasing, and that has an impact on our productivity. As the ambient temperature gets warmer, right, we sweat a lot, and we're not able to work as much. So there is now an ever increasing demand of cooling systems. It is sort of becoming necessity, like a refrigerator. Long few years back, the refrigerator was not common, but now every household has a refrigerator. Similarly, AC is also now becoming almost like a necessity. If you look at the statistics, they consume more than 40% of the overall energy of a building. If you take residential buildings, a lot of energy goes into just cooling these environment. The rest of it may be fans, bulbs, LED lights, the televisions, which is also LED, and computers. But the cooling system now, because LED is becoming more efficient, the cooling system is taking most of the chunk of the energy that we use in a building. So if we want to reduce, and the urbanization is going on very fast in our country, and with so many buildings, with high rises building, this is going to be one of the primary consumer of the energy that the country will produce. So we have to, I mean, if we want to reduce the energy footprint of the country, of the residential and urban areas, we have to look at the cooling systems. In general, there are two types of cooling systems. One is ducted, centralized cooling systems, which we find in the developed countries primarily. So if you take examples of the US and the Europe and anywhere which is developed, there is a centralized cooling system. In our malls also here and in big offices, you find there is one place where there is a huge compressor or a water circulating system, and then the air that gets cooled then is carried from that place to every room through ducts, through the pipes. Now what is centralized in here? There is only one place which is centralized. In every room you get a way to control how much air gets circulated, and there is a way to control the temperature, but we do not have the compressor for every individual room. The other ones, which is the primary topic of this particular presentation today, is ductless split cooling systems. So it is ductless because we don't have these pipes getting all in the building, through the shafts and through other places and from one place to another place. We don't circulate the air in the entire building, but we have a very small pipe running between two parts of the AC, the split part of the AC, one which is inside the room, one which is outside the room. In this context, we'll focus on this ductless split cooling system. Now, because it is not centralized, it is distributed, we don't have a way to control all these multiple split ACs. So let me take an example. If you're looking at a banquet or a wedding hall or a big theater, where in our country we at times install many small split ACs, okay, and we switch on all of them. But we have to control these every split AC in a very big space individually. Uh, we can't control all of them as one unit to optimize the energy. While in the centralized system, we could do that. The algorithm will control and see what are the temperature or what is the requirement, what is the heat load in every room, and we could control that. Is there a question? No? Okay. So now we'll have few more terms or terminology introduced. So in ducted centralized cooling system, what I'm saying is there is a compressor that distributes air to multiple individual cooling systems. So the one small panel that's there in every room, which controls the temperature and the fan, it's called individual cooling system, ICS. And in ductless split cooling system, each ICS is associated with an independent compressor unit, which is outside our room. Our challenge is an optimal control of this ductless split cooling system. At BITS also, we have many labs. We have a centralized system, but that doesn't cater to every lab and every office. In fact, some of the labs in the biology and chemistry department, they require more cooling on additional to what our central system is able to provide. It's little outdated, so it doesn't give us very efficient cooling. So people have installed split ACs on top of the centralized system. Now their usual way of running these ACs, and I've seen this in many uh, industrial systems also, like for example, corporate offices or banks, where they switch on all the ACs in a room with minimum temperature and let them run with maximum fan. That's the easy way of doing things. But of course, as you can see now, the room is very large and the heating load in the room can vary from one corner of the room to another corner of the room. The way AC vents, the split AC fans are situated in the room, at what place in the room, will have, depending on its location, different impact on how much air gets circulated in the room. Every AC can still be of a different make, manufacturer. Its energy efficiency could be different. The size, the tons, what we We measure the how much cooling we get from an AC in terms of tons, 1.5 ton, 2 ton AC, and so on. So every AC has its different capacity. Now, how do we reduce the energy footprint of the entire room in terms of individual AC consumption, but still get our temperature that we want in minimum amount of time? That's sort of the short one question that I will talk about today. And if time permits, I will also talk about another question, which is preemptive maintenance of these ACs. We running these ACs, they are running for a long duration in during the day and even night also, and they have issues in terms of its compression, the temperature setting, or just the room size. So what can be done so that automatically we detect these problems with the AC? I mean, one simple thing is it's not cooling enough. That's typically what we hear. But as in the networks also we say, right, I can't browse the internet. But to debug this problem, we need a lot of more information. And can we automatically detect if it's the AC is the problem, its setting is the problem, what is the issue? Or AC is going downline and will have a bigger problem coming up, right, later on. So that's the second problem, where we can find out the issues of with the ACs before we actually hit the lowest point. So we have multiple ICSs, these split fan units in a room. That's our setting. Uh, every AC has an independent control, and it has a different impact on the cooling inside the room. And every AC, because of its proximity or location in the room, will also face different heat load. Right, some AC will have more cooling to be done because it's just the warm air. For example, one which is next to a glass window and the sunlight is directly coming in, or more people are sitting in one corner of the room, or there are many machines, like for example servers running in one side of the rack, and that creates more heat load. So we have to consider all these challenges to come up with an optimal control. I'm showing you this diagram, this photo, where this is one of our data centers in the CS building. And there is, as you can see here, a centralized cooling on the top, but it's not sufficient because the amount of heat, like I was saying, getting generated in this small place was so much. Also, we can't run this centralized AC 24 by 7, 365 days. Right? And a lot of times this is down also, especially in the night when there are not many people moving around in the building. So we had these three split ACs on the right side installed on the wall next to each other, and they were cooling it. Now this is server rack. This is our ductless split cooling system or split ACs. And in center, you see these three LED lights, and then there is a box next to it also. These are our energy sensor. So what's an energy sensor? So there is power getting to the AC, but before the power comes to the AC, we in series install this sensor where it will measure how much is the voltage and how much is the current. So with that, we see how much is the power getting consumed by every individual three ACs. So we have three separate ACs, split ACs. For each one, we have a one sensor. So that's the energy sensor. We also have temperature and humidity sensor. So temperature sensor measures the temperature in degrees Celsius. Energy sensors gives us kilowatt hours, and humidity is measured in terms of percentage. Now, why humidity? Temperature we understand, right? Because we want to cool it, and if it's not cooling, we want to see, right, what is the temperature we have reached because of which AC. But humidity also has an impact. If as you know, in the coastal area, so for example, in here in Goa, the temperatures don't go high in summer as much as in Delhi or places on the plateau or in between in the country, but the humidity is some at times more than 90%. So combine I mean, if it's a 40 degree or 38 degrees Celsius, but with 95 percentage of humidity, we almost feel like 3 or 4 degrees plus. The humans feel this. So we also measure humidity with it. So this is another setup with, I think this is in the chemistry lab, where we have few more of these. So we've instrumented many labs in the department, and these are all IoT enabled sensors. What is IoT part in this? All of these sensors have 4G SIM installed inside it, and the data gets measured in terms of energy, temperature, humidity, and then it directly gets communicated via the 4G SIM to a server, to a AWS system, which is storing all of this, the time series data in a NoSQL database. And then from there, we retrieve it back. So these are energy sensors. That's air conditioner here. And I think I have one more example. This is very crowded place. On the left hand side, you see a lot of these batteries, which are powering up the UPS of this lab, and the batteries get very hot when they are charging. And the UPS also, when it's discharging, right, it gets heated up. And that's our energy sensor right there also. So as a system, this is live system. I will show you a page now. After this, I will have to move from presentation to a browser window where I can show you this live page. So as a data flow diagram, on the left side, the data gets generated from energy and temperature / humidity sensor. That's what we call data acquisition. Then it comes to AWS server, which has hosted MongoDB. And then from there, it comes to our system, where then we leverage this data to do a lot of measurement. So this is a dashboard. And let me just quickly jump to a slide. 1 minute, where I can show you the system running live. It's a share. So this is the live data of 3 ACs in room D250. And this is current month of March. And I'm showing you data here. This one particularly in showing unit consumption in kilowatt hours. And this is the average one for the month. And this is the temperature and the humidity. As you can see, the humidity values are different, temperature values are different, because every AC has different place. So you can see this particular temperature is saying at the bottom 26.31 degrees Celsius, and this has more unit consumption, while the one in the center happens to be at a good place. And this has a already sort of cool temperature, and it's not consuming much because most of the load is getting carried by the first AC and the third AC. So this is a live system, and we want to do it. We do it for multiple different rooms. This is live data. So now let me jump back again to our slides. Continue to share. Next slide. Okay, so let's now, technically speaking, let's see the problem statement. The problem statement that we have 3 parts. One is every cooling system follows a cooling cycle with certain maximum on and off periods. We can't let this AC run for a very long time. And the very simple solution is one AC has the maximum impact and maximum efficiency. And let's just run it 24/7, 365 days. But that will not be good, because that will reduce the overall life of the AC very fast. We don't want it to run off more than certain maximum threshold. The relationship between energy consumption and the change, the delta we see in the room temperature, that together gives us the efficiency of AC, and that is dynamic. From model to model, it changes from every day depending on the heat load that we see in the room. It keeps on changing. So that makes it complicated, because if we had a static relationship or a constant relationship, then the problem of optimization gets easier. Now, I'm not an expert in optimizations, multivariable optimization, or even these bigger statistical questions. Uh, but I will try to position this into showing what we learned from this live system and where we would able to make fair assumption, and that helps us solve the problem to right better than what's the current state of the art is. Now there is possibly maybe we can do more also, so that's still work under progress. We need a technique now that will first find out this dynamic efficiency of every ICS. And then based on these efficiencies, we want to compute a schedule about which ICS, which split AC will operate for how much time. As we increase the number of split ACs in the room, right, it should scale up. The algorithm that we come or whatever optimization we do should scale up with the number of ACs. Uh, so what things are existing or what we tried so far and what sort of works. One is linear scheduling techniques, which is we optimize the cooling system based on our prior knowledge of efficiency of each cooling system. So for example, if you buy these ACs very new, they come with the manual, the data sheet, and which tells us right how much is the impact of this AC, how much cooling it will do depending upon the new. But as you run this AC, the gas gets less and so on. In your setting could be different from where this energy ratings were derived from. But still, if you assume that you do this calculation once and then for the whole lifetime of these AC we will use just these numbers, then that can be used, and that solution would work. But as I've just said, the efficiencies of these systems keeps on changing uh, with many factors, for example, time of the day. So that's not a very optimal way of doing it. The other one now, whenever we see these dynamic systems and we sort of, it's unknown because these ACs will go into one room, then another room. Maybe I move these ACs, the room gets bigger. Uh, if I remove the partitions or if I add the partitions in the room, it gets smaller. I add more heat loads inside the room. Now, what we could leverage is reinforcement learning, where we are probing this environment with by running these ACs and see how much impact we see. And we keep on doing it. And provided at some time this is the environments get stable and doesn't change much, we will be able to derive the efficiency values. Right? So we tried this. These are compared to the first one, these approaches take time and they are slow to convert. So now question for this particular presentation is, can we do something which is midway in between these two? It's not constant efficiencies and we plan for the whole lifetime. Neither it's where we are starting from zero or scratch and we are right, and then we learn slowly and then arrive at optimization, because we want the room to sort of get cold very fast. As I was saying, I'm not a expert in this, but I will give you an idea of what we were thinking of. So one thing we realize while doing the experiments here is energy is how much energy gets consumed is a function of how much time or duration we run these ACs, the execution time of these units. So there is a linear behavior. The more you execute, right, the more energy it consumes, and right, and for a certain constant small amount of time. So now with this knowledge, if to optimize energy consumptions, we want to, the problem translates down to minimizing how much time we run these different ACs for. And the function that calculates the cooling system's execution time, right, is a convex functions of efficiency. If we check that with after data collection, and with that convex function, then it makes it possible for us to use MaXMIN solver with Bayesian predicting capabilities to define this as an optimization problem which can be solved. And then once we solved it, that means we get a solution which tells us right what is the minimum amount of time for which we run these different split ACs in a room. That becomes our schedule for long. Uh, can you hear me? Is it and see this?
Yes, yes, we can hear
Great.
you.
Thank you. Uh, so okay, I was here. So once so the time series that we are getting, temperature and energy sensor data or readings that we are getting, we calculate the efficiency. And once we have efficiency about which AC is running at what time, we use this time series to extrapolate this. So we identify this distribution with what is its distribution, and it's not a random distribution. These ACs are all right, well behaved. Uh,
Professor, could you please share your screen also because we can't
okay,
see
yeah,
the screen.
yeah. I
Yeah.
think because of that disconnect, maybe. Yeah, minute. Right. Okay. Now full screen. Continue. Okay. So we use the least sum of squared error. Essentially, we calculate the efficiency If it happens again, I will move to hotspot. So we estimate the efficiency of every ICS that's present in the room, and we learn the probabilistic distribution using the square of the error method of the time series, and that gives us what will be the distribution. Now, once we have understood these efficiency, time series efficiency and its model, we use probabilistic regression to generate the long-term strategy. As I was saying, then we use this probabilistic distribution with regression to estimate the future efficiency of the AC. Once we have these values of every AC's efficiencies, we use the MaXMIN solver to find out among those ACs what is the minimum schedule that we have to run. So that means which AC has to run for how much amount of time, and that will get us to the temperature that we want in the room. And in parallel to this, like I was saying, we don't want to be right greedy in the sense just use the best AC that I have continuously. So we uh, create an automata of the AC in parallel, which is like a digital twin of the AC to see which AC has been running for how much amount of time. And we don't want to overstep or overuse one AC so that right, we don't damage that particular compressor. So that's our solution. Now, how do we want to evaluate how good works? Of course, first thing we have to find out is right, which is the best schedule in terms of energy consumption. So how do we evaluate this? We do it in both because we have the luxury of a test bed here where we have instrumented one or more rooms with actual sensors, and ACs are running with those sensors, and a production environment. We don't control it, as in, although it's a test bed, it's a live, it's live test bed. That means we don't ask people to go in, come back, and we change any of the heating load of the room. It is what it is. But with that setup, with that many AC, we can do an experiment to find out how much energy gets consumed and whether that can be reduced further. So that's our experimentation. The other part is the simulation. There are simulating tools available. Energy Plus is one popular one which is accepted in the community that allows us to create a virtual building with different square feet of every room, and we can put place heating loads inside this room. For example, how many people, how many machines, and what is the temperature, ambient temperature outside, how much sunlight is coming in, and so on. and that allows us to create more or bigger setups, because our test bed has, the one that I showed you has 3 ACs, but right, we can do far more ACs in a simulation. For comparing our solution, we select the two approaches that I told you about. The one which is linear scheduling, where we know the efficiencies, and then those are not going to change, but we can find out using linear programming or something similar to that, and find the best optimum schedule. The other one is reinforcement learning, where we put these agents in the systems which are probing and learning these efficiencies of the AC slowly, and then we use that to decide on a schedule. And the third one, which is the topic of the presentation, which is what we call model assistant. Uh, the metrics for the evaluations are estimation of the efficiency. So how good, before we jump to the bottom line, which is energy, we are going step by step. So first thing is, because we are estimating efficiencies, how good we are in estimating efficiencies as compared to reinforcement learning. So we will compare that. Then the bottom line, which is the energy consumption. That's what people care about, right? Whether this particular scheduling strategy or scheduling particular schedule is reducing my energy bill or not. So we'll compare that. And then it's not just the energy that is important. We also want to see whether that technique or schedule that we come up with, is it able to maintain that temperature. It should not like, overall the energy consumption is less average, but maybe the temperature fluctuates so much in between that it's not good. um, so we want to see on an average, oh no, what is the temperature maintained, whether it actually diverts a lot from the what we want, and the time taken to cool the room. uh, we I mean, as much as possible, we of course want to cool this room faster. We don't want to, I mean, the schedule is such that eventually, after a long time, it will get you to that temperature with minimum energy consumption, but it takes really long time. We also don't want that. So we measure the time taken to cool the room and the temperature that gets maintained inside the room. So this is the first plot. On the x-axis, you see time in minutes. I'm showing you the data of 1 hour. On on y-axis, we have the efficiency, which is a ratio with each technique. And then we have 3 techniques. One is the linear scheduling, which is what we say CLA. So those are the boxes. And as you see at the bottom, it's constant. We just take the efficiency maybe from the data sheet, or maybe one short experiment, and then we keep it constant for the lifetime. Okay, so it's not changing. It doesn't say whether this is correct or not correct. It just says it's constant. We don't change it. Now the other one is the third one with the stars. That's the reinforcement learning. And if you see here, it starts way off from the actual efficiency, but it from there it starts getting better and better, and it comes down. So this is, and it keeps changing, which shows us this is dynamic and we need to keep on measuring it. So this is what, right, what we can think of it is, this is the optimum efficiency value which we can derive, because this is constantly learning without any assumption. Now what we have is the with the time series data, with the linear regression, and then projecting it, extrapolating values. But so this is away from the constant, and but it also comes to a good value, and then it stays constant. Now overall we are little off. The the model assisted is off from the reinforcement learning efficiency, but it close to that, better than the constant one. That's what, right, our aim was when we set out to solve this problem. So that's estimating of the efficiencies. This is in an experiment, which means this all these ACs are real, right? The sensors are real, the data is real, and we executed it on that. So it learns it faster, and then it keeps changing, not as much as the reinforcement learning, but sort of good enough. The next one is how much energy gets consumed in terms of kilowatt hours. Now, here on x-axis, again the time, and then the y-axis is energy bill, the number of units we are consuming. So here, the minimum energy consumed is this square brackets, the line with squares in between, which is the reinforcement learning. So this is not about bad or good or correct or incorrect. This is the minimum energy consumed, right? So the reinforcement learning does the best. But also our one, the model assistant is also sort of going close. At times reinforcement is really low, but it takes a long time. It takes some time to come to that value as compared to the linear constant scheduling, which is above our algorithm. That means you can't do a very simple calculation of one time estimation of efficiency and just live with it for the whole duration. So there is still scope. Initially, for first 20 minutes, we were close. Then at this point and at this point, we were away from far more than the reinforcement learning value. So there is still scope of improvement, and that's something we are working on. The third one is temperature maintained and the time taken to reach the set temperature for the first time, right? So so we are desiring temperature of 23 degrees Celsius in that room. So we said, and then now let's see. So all three are able to do it very close to 23. The one that we have was able to get 23.3, which is sort of the optimum one. OCSR was 23.5 and this one was 23.8. The other one here, because CLA is doing linear scheduling, right, and OCLR has, it takes time to learn the efficiencies. It took 18 minutes to reach that temperature for the first time. So reinforcement learning has, we have to give some time for the reinforcement part to kick in and get its first value out, while model can do it faster and can is as good as the linear schedule in terms of reaching that temperature. So this is a setup, a simulation setup where we had far more rooms. Yeah, I forgot, I should have mentioned how much was the heating load and so on. That's in the paper, but unfortunately I forgot to put it here. Uh, so looking at this again, x-axis is time, y-axis is efficiencies, and these three algorithms are executed here. Uh, we have to zoom in. So on the left side, you see a plot, and then I zoom in the first part. So on here, it's 1 to 4, but on this side, it is 0 to 1.5. So if we zoom in, the reinforcement learning comes from the very top, while model assisted was able to get us quicker to these values initially, and then it came close to the reinforcement learning, and then it sort of went close to each other. So model assisted also was able to get the values faster when we put it in the simulation. For energy consumed, I'm adding one more time series data in this plot, which is GA. So this is a greedy algorithm. What is greedy algorithm? This is theoretically optimum possible. We do away with that assumption of we can't run this AC for more than certain X duration. Let's see if we are in a hypothetical world where we just use optimize the energy consumption by putting all bets on or putting all money on the best ACs that we have. So that's a very greedy approach, and it will result in the damage, but it giving us what is the minimum energy consumption. So if you see here, with this is a new dotted line, that is the minimum now on an average. At certain times, reinforcement gets at no, the MAC algorithm gets us lesser than this, but on an average, greedy is the best one. So now here, if you order this time series data, the best one is greedy, then the reinforcement learning as expected is here, and the model assisted comes close to the reinforcement learning and at certain times close to the greedy also. So in a simulation environment, this worked out to be very good for us. And the linear scheduling with constant efficiency estimation is still way off. It's more than all of these. It's above. So that's our energy consumption for the greedy in comparison to the greedy, and we did better. The third one is our temperature maintained and how much time it takes. So the average temperature is close to 24. That's what we, I think, set or we want to achieve. In here, our model assisted one was able to get 24.3, while the greedy was able to get 24.9. And why this is more is because greedy will not use all the ACs, and some ACs in some corners will never get used, and that on an average in the entire room you don't reach that temperature. Okay, while the linear scheduling use all these ACs in circulation, and so the temperature gets on an average set to or close to our set temperature in the room. So we are doing as good as the linear scheduling. Time to reach the desired temperature, greedy is just taking long time. It's again, the reason is the same. Some corners of the room just left out. We never use those ACs because maybe its efficiencies are not so good in comparison to other ACs, and so it takes really long time. Uh, the model assisted is close to the linear scheduling, and of course, because reinforcement learning will take time to learn the efficiencies, and it takes more time for that, so it's taking 52. Now, these are three different ACs which we separated out in this in particular simulation. So, and then we also give these different temperature in terms of environment. So when the outdoor temperature was 38, 20, 32, and 26, and we want to achieve 24 degrees Celsius, how much was the energy consumption, and how much was the time taken, execution time. So for 38 degrees Celsius, it took us, of course, more time, 1696. But this is very close to the reinforcement learning. Here also, we took 1548, and then here we took 1404, right? And we are always competing with the reinforcement learning in terms of how much time the AC gets executed with the schedule. So overall, if we have information about the model of that AC, the time series, then we leverage that linear relationship between the efficiency of the AC and the temperature that, no, sorry, the efficiency of the AC and how much time the AC runs. If we know that there is a linear relationship with that, then we can learn the efficiency. If we learn the efficiency, then we can extrapolate that. And then with that extrapolation, we can come up with a better schedule compared to the constant efficiency or efficiency learned using reinforcement learning. So for this particular problem statement, that we are still dealing with dynamical efficiencies. It's not constant. So the heat load in the room can continue to change, and our probabilistic techniques is able to deal with it. We combine those techniques to learn the efficiency with the optimization framework that we have, and was able to get that schedule very quickly for the AC without waiting for the reinforcement learning to work. And our optimality comes very close. We are not exactly at the reinforcement learning because that's the most optimum one, but it takes also computationally and time wise, it takes more time, but we are close to that. And overall, we observe that this knowledge of the AC and how it functions can help us, because that gives us more understanding of how the time series of that AC works. We're able to save about 30% of the energy in getting that set temperature that we want quickly, and right, maintain it overall in the building. So that's one work. And I also, how much is it? So how much time do I have more? If some time permits, I can
You
maybe
have time till 6.
six, na? So
Yeah.
let me shift gears and show you another thing. But before that, all collected for this started really during the COVID time, and it was very difficult to do the experiment, but we were able to, once the instrument sensors, the sensor also helped us in the COVID time because nobody would actually go to the data center, and because it was all locked down, and the temperature sensor at times gave us warning like it's the temperature, it's not cooling, something is wrong with the AC, or the water is leaking from the AC, and so on. And because of that we could save our servers, so that was another benefit of the entire system. But yes, we collected this data for a long time, and this is all uploaded in data.gov, and it's public. It was we got money from ACM SIG Mobile community to run this. So all the money and funds came from the ACM SIG Mobile competitive grant, and we leveraged that. And then, right, because the money came from the funding agency, we decided, okay, once we publish this, let's make it public. So it's all online. If you are interested, you can scan this QR code. It will take you that page, and then you can download the data that we have, all these ACs. Now, the second question that I want to show you here is the preemptive maintenance of the AC. Okay, I hope you are able to see the slides. So, okay, let me jump to, because we have 15 minutes to a slide. 1 minute. Yeah. So, one of a bigger question.
We can't see the
You can't
slides.
see, no? Okay,
So,
1 minute. Thanks. Mm, yeah, right. So the problem here is, let me go to a full screen mode. So the problem here is we want the ACs will have issues. Sometimes we complain the temperature is not so cool. It takes long time to cool, and so on. The unit consumption that we have, AC is actually giving us far more bill in utility than I expect. I don't know why his AC is better than my AC, and so on. Should I buy a new AC? Is it the sort of the best I can get from this AC? Should I move to a higher tonnage? And many questions. Sometimes the preemptive maintenance of simple cleaning, right, helps save the bill, and get us also right before the bigger fault happen, that we are able to rectify it. So we divide this entire problem into three stages. One is first identifying the anomalous instance. So the behavior which is not matching the expected or the normal average. What is anomaly in this entire behavior? Okay. So we are collecting because we know, and one of the important factors of your pulse on the AC is how much energy it is consuming, how much temperature, and how much is the humidity in the room. Because once the AC starts running, it also dries out air. So humidity, temperature, and the unit consumption. And with these three, we have something which is expected for your AC. And if any time the AC starts diverges from this regular behavior, we call it an anomaly. Right. So if the energy consumption, for example, deviates by 5% from the energy rating, right? Energy rating is what we see in the data sheet. Then we call it anomaly. Now, once we see that there is an anomaly here, then what are the types of anomalies? So we classify these into three categories. One, what we say, we have set the wrong temperature, and what you are expecting is not going to happen. Second thing is there is some technical fault in your AC. And the third thing is the cooling requirements are not getting satisfied. And so what you are setting it out to achieve, it's not happening. And we have simple rules, sort of a decision tree, where we take this time series data and then we apply these if then else condition rules. And then that tells us whether you're falling into first cause, second cause, or third cause. Once we know that, the second challenging question is the technical fault. Now, if there is a fault inside your AC, then what are the parts? There is condenser, there is expansion wall, there is air handling unit, which is sort of the fan, there is evaporator, and there is a compressor. And on the x-axis, we have different energy consumption of this, and then there is temperature, and this is where it falls. So so if you see, you can think of this as clusters, and if you are able to find if there is a fault, then right, if it falls under certain cluster, then there is a fault in that particular component. If there is a, if your measured value fall in the cluster, the yellow cluster, we will say there is something wrong with your air handling unit, and so on. So if we can write a classifier that can do the clustering, and then we measure the data from your AC, and then we plot it back here, it can give us an idea that where is the fault. Now the question is, how do we get this plot? Every AC is different, every room is different, and every heat load that we will generate is dynamic and different. So what we do here is, people have run this again like reinforcement learning, collected lot of data. But even if you collect a lot of data, it's very difficult to inject these faults in your working system. It's something which is in production, it's working, right? And damaging those, it's not going to happen. Maybe the AC companies will do it that way, but it's very difficult to do that. So what we did is, that's where our simulator came handy for us, the Energy Plus. And we knew in the simulator, we actually have a software version of all of these, and we could inject fault in this. And then the data that we got out of the simulator will have these temperature and the energy consumption with that particular fault in operation. Okay, so still it's not the real model. It's the model that we learned from the simulator. Now, then if I buy AC, it comes with a data sheet. Now I did transfer learning and was able to uh, transfer this entire plot, sort of do a mapping of this entire plot, but for the model that I have. Okay, so I shifted it with the parameters that I know that goes in the simulation, and then if the values of the AC that I have are different, then I was able to project it into that different plot, and then have the entire same plot for the AC that I have. So this reduces the time it takes to do the learning of the faults. And that was the principal idea. And we decided, okay, let's give it a try. Now that we have these ACs here, uh, we try it out. We transpose this model, do the transfer learning, and then see how good it is behaving. Okay. So then we did the DB scan is an algorithm which can find out the clusters for us, and we leverage that. And let me just directly jump to the algorithm. So we tried different clustering techniques, and uh, we knew the faults that were there in actual practical also, some for some of the ACs, and the algorithm that we had came out to be better than. So this is just comparing the different clustering techniques, but the one that we have is sort of giving us the 0.8 accuracy score and F1 score of again close to 0.8. So it worked out to be good. Uh, so this is giving us an idea where whenever there is a lack of data that you have, we could learn a model in a different setting and then do a transfer learning. And then the good part is we still were able to detect these faults to a decent accuracy. Not perfect and not all the faults, but the ones that we set out to detect, we were able to detect it in a better way. Here again, the data that we had came in handy. So overall, uh, that we are working on this problem here in our setup at Bigs Goa, because more and more rooms are getting instrumented with a lot of split ACs. So first thing we want to do is reduce the energy consumption, the carbon footprint of the building by giving out the schedule where we decide which AC should turn on at what temperature, at what time. and then reduce, and without right compromising on uh, the, the 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 ambient temperature that we want inside the room, get the bills to a lower value. And then because we sort of know the normal behavior of the AC, any deviation from that is an anomaly. And then if there are certain faults in right, we can detect those faults and then call the technician and give this data to the technicians, so the technician can right, quickly come and get the fault repaired. So that's the overall idea of the work. I think that's all I have. I think we still have about 4 minutes. Maybe I can take questions if that's the.
Thank you, Professor, for an informative talk. I request the audience to ask your questions. Okay, since there are no questions, I guess I would like to end the meeting. Thanks again,
Okay.
Professor. Thank you, everyone, for attending. Have a great evening.
Yeah, yeah. Thank you for inviting me. Okay. Bye.